Hello and welcome to today's episode of our podcast. We are thrilled to have with us Ananth Mahadev. He brings us a wealth of experience and expertise in FPGA design and hardware engineering. He is currently a FPGA engineer at Eviden, where he have been working on the forefront of designing advanced systems. Prior to this, he held a role of senior hardware design engineer at Tata Elxsi, where he contributed significantly to cutting edge hardware solutions. He have a strong background in research, having worked as a junior research fellow at DRDO's Naval Physical Oceanographic Laboratory, where he supported mission critical defense projects. His journey into hardware design began as an intern at an Embright Infotech, and since then he have developed wide range of skills. We are excited to dive into experiences and insights on FPGA innovation in defense domains, as well as explore the broad impact of FPGAs on various industries. Let's start. Would you like to introduce yourself from?
Yeah, thanks Anushka for the introduction and thanks for having me here today. So I think I'm audible enough for everyone. Hello, hello.
Yeah,
Yeah,
yes.
yeah, sure,
Yeah.
sure, sure. Yeah, thank you. Yeah, so
Yes,
basically
audible.
I'm. Yeah, yeah, thank you for the response. Basically, I'm an FPGA design engineer, and my basic job involves designing and development of basic RTL designs in FPGA and delivering it for high performance applications. And currently, I'm working with Eviden, an Atos business. It's a French MNC, and I'm based in Bangalore. And as for my intro, Anushka had given you the work experience. So I have done my master's and in VLSI and embedded systems. So that's where it all started. And I'm a bachelor in electronics and communication. So from there, I started working on the FPGA field after doing my master's. So to kickstart with, I know that there are many people who are from electronics background who have joined in this call. So I would like to give you a little bit of introduction on VLSI, which is something that forms the basis for FPGA design as well as ASIC design. Then we will proceed further with the FPGA based aspects and as well as the mainstream topic of today's podcast, which is defense applications using FPGA. So VLSI, what we always understand about VLSI is most of the people will think that VLSI is nothing but integrating a number of transistors inside a single chip and then using it for a particular purpose. It's as simple as that when we explain it, but it's much more simpler when we look around us. So, for example, when we take a look around us, we can see most of the electronic equipments that we are using day to day. It has a VLSI based design or a device that actually powers it. So, for example, let's take the case of the laptop we are using. It has a processor like the general purpose Intel processor or the AMD processor. Then it will have a graphic processor or the GPU that is powered by either AMD or NVIDIA. Then, if we take the case of the most common device that we are using, that is the mobile phone, it will have a processor similar to this. So all these comes under the VLSI because VLSI is a very vast domain that supports most of the design, verification, translation, validation, testing, verification, everything. So how we can actually use VLSI in our day-to-day life is simple as that. But when we talk about VLSI, VLSI has two main elements to be discussed. So the first thing is the perspective, that is how we perceive VLSI, and the second thing is how we are actually modeling the design. That is how VLSI design flow works. So in case of the perspective, in the two pioneers or two major engineers, two veteran engineers who lived in the 90s or beyond that, they actually delivered a particular approach in checking out the perspective of VLSI design, and this is called Gatsky-Kun chart. That is, it's called like that, but it's generally in industrial terms it's called Y chart. So Y chart is actually delivering the perspectives used in VLSI, and the perspectives that are basically used are of three types. The first one is behavioral, then structural, and the third one is physical. So all these converges to the final entity that we call as transistors. So in behavioral terms, it is more like we will be checking the perspective from the side of an algorithm or from the side of a signal, like that. But in terms of structural, we will be focusing more on the processor level approach, the flip flop level approach, like that. And in terms of physical, we will be checking how the device is actually operating. Like for a processor, how the physical layer is implemented, how each and every layer contributes to the final device. And it all converges to the transistor, because we know that the transistor is the ultimate building block of any VLSI device. So now coming to the design flow of VLSI, I will just briefly give you an account so that it doesn't bore you at all, and it will be interesting for you. So when you are coming across a problem, for example, assume that you are given a problem and you have to create some sort of a specification for a solution to that particular problem. So that kind of thing is the first element that we will consider when we are actually going through the VLSI design flow. For example, we will be addressing a problem, and at the same time, we will be trying to figure out what all specifications can we put in for actually solving the problem. So these specifications are initially discussed and finalized before proceeding for the solution using the VLSI design flow approach. So the specifications are the first thing. Now, coming to the second scenario, that is after we have clearly defined that these particular specifications are necessary, the second scenario is that we have to translate this into hardware, right? So that is the ultimate aim of this particular VLSI design flow, and we have to finally have a hardware level solution for this. So how we will translate? That's the first thing. So for that, we have to take support of some softwares, and softwares help us in translating the specifications into a particular hardware. So it will act as an interface. And in almost everything, the softwares are actually the mainstream elements that will support in testing, validation, etc., etc. So the first thing is that for creating a particular software-based model of the particular specification, we will actually try for two approaches. That is, in ASIC design flow, one approach is followed, and in FPGA design flow, there is another approach. The ASIC design flow approach is like we will be directly going for the RTL level design based on the specification. And RTL design is the next step, which is the start of the design entry. So I am now sectioning the specification as first we will specify, second we will go for the design entry. So in the design entry, what we will do is we will be writing codes for equivalent elements or digital elements that can actually function as per the specification that was provided. So in RTL, how we will do this is RTL is nothing but register transfer level. Okay, it's a behavioral approach. So RTL is register transfer level, and using this method, what we will do is we will be making use of hardware description languages, HDLs. You might have heard of this. HDLs are of many types. Like you might have heard about VSDL. You might have heard of Verilog, System Verilog, etc. So these particular languages we will make use, and we will write codes which are equivalent digital circuits of these particular specifications. And but does the problem solve there? No. We still are sticking to the software level definition of our specification. We need the hardware. So how will we go further? So first we have to check whether whatever code we wrote is functionally correct. Is it working functionally or not? And also we have to ensure that whatever we have written is optimized to the best, so that we can get best performance, best chip area or resource utilization, and best cost effectiveness, best power usage, and also the final thing is best frequency or maximum speed. So all these things we should consider, and then we should produce a particular design. So for that, in the design entry step itself, we will do simulation of the code that we have written. And once the simulation is done and all the parameters are working fine and the functionality is verified, and we will do a re-optimization iteratively. And after this optimization is done and the functionality is verified, we will proceed to the next step, which is called synthesis. Design entry, first specification has happened. Next is design entry. Now we are going to synthesis. What is synthesis? Synthesis is nothing but we have all we have now is a code, and that is functionally valid. But we need this to be translated into a particular hardware level description or hardware level entity. And that is how this translation is done using a synthesis tool. So in ASIC design as well as in FPGA design, synthesizers will actually translate the code based on the IEEE standard libraries, and then they will generate a particular element called gate level netlist. So now we are actually talking about gates. So we have come from RTL level codes to gates. And now what we have is, when we have written, like I will give you an example and explain, that will be better for you to connect. For example, you have written the code for a full adder. So now when we are translating, we will be translating this code into gates. So it will have this many number of gates representing the full adder, right? So that is what is happening in synthesis. We are actually promoting the entire code into a gate level netlist. So once the netlist is also ready, we will now proceed it for optimization, further optimization of the netlist. So the netlist is optimized differently. And once the different optimization steps are done, the final netlist which is optimized is produced for physical level implementation. And this, in between these steps, we are iteratively verifying whether our design is actually performing the best, is consuming lowest power, whether it's consuming less resources, and is working at the necessary speed that we need. So we will do iterative process. It's an iterative process. It's always repeating. Once the RTL logic is finalized, always this flow will be repeated. And once the synthesis part is complete, and what should be the content of design specification? I think Brunal has asked a question. So that could be defined based on how the design team sees it. Basically, how they are trying to involve in providing a solution to the design or the problem. Sorry. For example, you have a problem where you are trying to generate a signal processing architecture or a signal processing module that takes in n number of sensors, or maybe 5 sensors, let's say 5 sensors, and they are trying to run an algorithm. So they will be checking what kind of device and what kind of approach we can take in, and which algorithm can we use. All these things will be provided in the specification. So and most important thing about this is that you should all, when you are starting your journey as VLSI engineers, you should all have a research-based approach rather than just becoming a designer, because research-based approach improves your designs over time. And initially, for example, when I first wrote a VSDL code, it was very bulky. Like I wrote a full adder code, it was bulkier than so many lines were used and so many resources were wasted. But nowadays, when I write a code about a full adder, it will be much lesser. It will look neat and it will not consume that many resources. There will be methods that come up based on your experiences. So that kind of approach you should have when you are actually specifying. Specification should be very strict so that you are clearly defining what solution you are going to implement. Okay, so I hope that answered. But now continuing with the netlist and the physical design. What is physical design is nothing but, now you have a netlist. Still it is in software format. And the physical design, now you are translating it into the technology. That is, for example, when I'm talking about technology, you might get confused. The simple thing I can say about technology is, you might have heard about 7 nanometer technology, 4 nanometer technology. TSMC is testing 1 nanometer technology. Like that, you might have heard news. If you check LinkedIn or if you check some forum, you can find these news, or even in the worldwide news, you can see this. So this technology node is nothing but, it is the channel width that is actually used in the transistor. So when the channel width is actually less, the technology node becomes faster. It becomes more packed, like you can pack more transistors in a single chip, and it will provide you more performance. So that is how the technology node, when it goes down the line with the years, it is actually providing high performance and high parallelization. So mapping the netlist to the technology is what we are going to do in physical design. So physical design is nothing but we will be starting with a floor plan in terms of ASIC. I know this is a bit confusing for most of you guys, but I'm trying to generalize it because our importance is on FPGA. But I will just quickly wind it up because VLSI design flow is more of ASIC and FPGA design flow is more of a tool-based approach. So in ASIC design, what we will do is we will actually go for we are actually designing the chip, right? So in ASIC, we will actually develop a floor plan constraining the area of the chip, and along with that, we will do flow placement. We will place all the particular IPs that we have developed or the modules we have developed, and we will place them in particular arrangement, and then we will proceed for the routing. So floor plan, placement, routing. All these steps are coming under the physical design. Now there will be verification in all these steps. And in ASIC design, there is one more step which is called clock tree synthesis. This step is very crucial because we need to ensure that in sequential design, all the clocks are reaching the point without any delay in between them. There should not be any clock delays that are causing any kind of timing disruption in the design. So clock tree synthesis is a step that is actually done in physical design. So in contrast, all these steps are coming under physical design. There will be iterative verification, testing, and validation done, and there will be optimization in terms of timing as well as area and power. So all these steps, once it is done, we will proceed to the final step of fabrication. And fabrication will be done, and the chip will be coming out as per the fab or the taped out of the fab. And the first chip will be the prototype chip. It will not; they will not directly fabricate the entire chip together because that will cost you a lot. And if there is any bug in the chip, then you have wasted a lot of money. So that kind of an approach is something that they will do. They will prototype one chip, they will test it as a black box, and then they will test it iteratively. And finally, if there is any bug, they will do the iterations again. That is, they will start from the flow where this step has been identified as a bug, and then they will proceed with the same thing. So once everything is finalized, there is no bug in the chip. They will actually go for manufacturing it in a higher, like a more number of chips will be manufactured together. So this is how they market ASICs. Now, so I hope you understand. If there is any question, you can ask.
So, no questions right now. So, what is the difference between ASIC versus FPGA flow?
Okay, so yeah, that's a very good question. That's a crucial question actually. The first difference is that after specification in most of the ASIC design flow, we will not be directly generating golden reference images or golden reference models using mathematical approaches because FPGAs are more constrained with the behavioral approach where we will be designing algorithms and we will be delivering it in the FPGA as image files. But in terms of ASIC, it is not the case. We are actually developing a chip. So ASIC is development of a chip, and FPGA is development of a design or a solution that on a chip that is already there. So that difference exists. So after specification in FPGA design case, we will be actually adding. This is a basic rule that is followed across the world. You can find it in a textbook. I have already shared that textbook with Anushka. That is the thing is FPGA. What we will do is if we are trying to implement an algorithm or any kind of design, we will have a mathematical model initially that will be developed in MATLAB, C, CPP, or Python, etc. And after that only we will be proceeding with the later on steps. But and also there's a difference. That is, in case of ASIC, we are doing a physical design and we are developing a floor plan based approach where we will be designing the chip. But in FPGA, we are not doing that. The chip is already there. So what we will do is we will be changing how the netlist will be implemented in the FPGA. That's the difference. So the design will be mapped into the FPGA, whereas in case of the ASIC, the design is actually developed as the ASIC. So it is kind of like the architecture is made into the ASIC, whereas in case of FPGA, whatever code you have written, it is actually mapped into the FPGA itself. FPGA is already there. You are actually mapping it into the FPGA as design cells. So that is the major difference. And the output of ASIC design flow is could be a 2D based GDS2 file, That is a graphical file that represents the multiple layers of ASIC that can be given to the fabrication. And the final output product is the ASIC chip itself. Whereas the FPGA, the chip is already there. We are actually configuring it in such a way that it will work as a signal processor, or it will work as an adder, it will work as a subtractive, whatever you are designing. FPGA is configured like that. So I hope that answered your question.
So, we will take these questions afterwards in the Q&A. So let us move forward. So what would you choose, FPGA over an ASIC for a design and vice versa?
Okay, that's a very good question actually. So before answering that question directly, I will indirectly tell you what FPGA is, because FPGA is something that we should always understand. FPGA means field programmable gate array, and ASIC is application specific integrated circuit. In the early stages, ASIC was superior to FPGA because FPGAs came into picture only in 1985 when Xilinx developed their first FPGA. Okay, so FPGA was also called as a fully reconfigurable ASIC in the earlier stages. But later stages, FPGAs were having multiple options that changed it from a pure fully reconfigurable ASIC behavior. Okay, so I hope that is clear. And now talking about FPGA, let's put in some fun elements here. Most of you might not understand directly what an FPGA is, so I will just relate this with some real life situations. So I will give you 4 examples. Two of them very silly example, and two of them very straightforward examples. The first example is, you might have seen a show called Pokemon. In that, there's a Pokemon called Ditto. Ditto is nothing but a Pokemon that can replicate another Pokemon in physical form as well as its attack or powers. So FPGA is like that only. So if you want FPGA to be a signal processor, it will actually work as a signal processor. If you want it to work as a different ALU or arithmetic unit, it will work as an ALU. So that is the flexibility that FPGA has. Now talking about the second example, you might have seen, like, who hasn't seen Pokemon, I will relate another example, that is Venom. Venom is another movie from Marvel. Venom is like that only. It has a particular biological effect called symbiosis. That is, Venom, when it attaches to the host, it actually assumes that all the powers of the host are enhanced, and Venom assumes that. So, like that only. So, if Venom attaches to a human, it has the IQ of a human, and it has an enhanced value. So if it attaches to a horse, it is like a horse, but it is a more powerful horse. So like that, FPGA is only. Whatever design you are providing, FPGA enhances its capability and performance, and it will work like that. Now talking about the real life examples, Lego. Lego is another example. Lego is like, you have small building blocks, you will combine them and you will form a bigger design, like a model. So like that only FPGA. There are small building blocks which I will be explaining just in few minutes, and you will be combining them in different formats and you will be generating a model. So that is another example. And the most important analogy that I can make, which is very similar to FPGA in real life situation, is octopus. Octopus is the best example that can relate you with an FPGA. The reason being, octopus is the only animal that has 9 different brains. That is, each of its tentacles has each one brain or a neural network that will actually access different cells in that particular tentacle. So, like that, FPGA, and it can adapt to any situation. So, FPGAs can be reconfigured in any format, and it can adapt to any situation without actually changing the hardware level constraints much. So that is how I can relate FPGA. Now coming to your question, which is like how we choose FPGA and ASIC. Let's take the case of defense itself. Defense equipments are not produced in mass, right? You will not produce so many equipments together. You will be producing a very limited number of equipments. That is why we have a limited number of jets in sky of a same manufacturer or dealer, and also in terms of submarines or warships or anything. So other than properly used manual weapons, whatever weapons or systems that have electronic warfare, these things will be developed in a very limited number. So FPGA, when you are using an FPGA, you are actually saving cost, cutting cost. The reason is, if you want, let's say, take the case of a satellite. A satellite is nothing but you are spending so many million or millions of rupees and you are launching it into the space, right? So once it is launched, you do not have the option to go there and change the hardware. Is there any option? No, right? For that you have to spend another set of millions and then come back. That is not possible. That is very silly thing to do. But in the case of FPGA, if you are putting an FPGA there and then you are uploading an image or a bit file from here, then you are actually changing the settings without even touching any hardware and without even spending a penny, right? So that is how FPGA becomes an advantage. Whereas if you put an ASIC there, you have to do a different set of command operations. You have to reboot. You have to change the instruction set. You have to do so many things. I'm not saying I'm against ASIC or anything. I'm just saying that FPGAs have that reconfigurability at a lower cost. Okay, so that is the advantage of FPGA. I've just given one example. Then another advantage that FPGA has is FPGA is programmed using a bit file, right? As I said, FPGA design flow, in the end, whatever design we are developing, it will be generated as a bit file. Okay, in the end of the design flow, one bit file will be generated, and we will be loading this bit file or burning the bit file into the FPGA, and the FPGA will be acting as the design from that point onwards. And burning a method is having like you can burn it in different ways based on the memory which you are using. You can use flash, you can use SRAM, you can use there is one more type of FPGA where one-time programmable. You can actually program it once and that's it. It's gone. So some FPGAs are like that also, and that is basically used in some destructive applications also. So these kind of things are there. But let's take why we need an FPGA. Why not use an ASIC everywhere? First thing is cost. Second thing is FPGAs have high parallelization. Okay. For example, let's take the recent news. We have seen Israel having a conflict with one of its neighbors, and we have seen how Israeli defense systems are actually terminating their attacks or interfering with their attacks using one of their most world famous system, which is called as Iron Dome. Okay, Iron Dome is nothing but a missile interceptor. Okay, so it is working from ground. It has a base station. It has multiple base stations basically, and it always keeps on surveilling. So it has an active surveillance, and it will always cover the entire area and check for any active threats that are coming into the scenario. So this method is actually the best method to actually interfere. And for that, we need parallel inputs to be handled, right?
Yes.
Yeah. So what happens is when parallel inputs are something that we need to handle, we will actually make use of an FPGA instead of a microcontroller. The reason is microcontroller has a fixed architecture and there's a stack that will actually push each instruction sequentially. But in case of an FPGA, it is not like that. You have multiple blocks of design working in parallel at the same time. So for example, there is n number of sensors connected into the network, and your FPGA is drawing data from all the sensors together, and then it is processing all together and finally delivering a particular output. So these kind of approaches are very much interesting and valid when you are using an FPGA. So now putting an analogy here, assume that I play violin. Okay, and I play violin and I'm trying to make a song. So now assume that another orchestra is there and they are playing the same song. So how different it will be? Like if I'm playing violin and handling only one task at a time, but you are also listening only one thing, one particular or like instrument at a time. But when you talk about an orchestra, you are listening many things at the same time, and many frequencies are coming to your ears, and it is sounding more melodious, right? So that's the same thing that is happening inside an FPGA. You are running parallel processes, and it is kind of like a threaded architecture because FPGAs have an architecture where the fundamental building block is called as a configurable logic block. This term is from Xilinx. Then there are other terms given by each and every vendor. Okay. So this configurable logic block is nothing but it will have LUTs. You might have heard of LUTs. LUTs are lookup tables. So lookup tables are nothing but if you have a particular design, for example, as I said earlier, full ladder, you will have all the combination of inputs and its corresponding outputs. And this will be stored in the LUT. So the advantage is when you are having a particular combination of input, the LUT will provide the particular output. So this connectivity or this mapping is done inside an LUT, and this is present inside the CLB. And along with the CLB, there will be interconnect network. It's a fabric. So there are multiple CLBs, then there are fabrics, and when the bit is programmed, what happens is the CLBs are activated based on the design that you are inputting, and as well as the connectivity is also activated based on the switching. Like you have one particular full ladder here, you have one particular full ladder here. Output of this full ladder will go into the input of another ladder. Then you will be interconnecting them, right? So that will happen inside the FPGA when you are programming the bit file. And I would suggest most of you to try this out yourself when you are actually trying to build an FPGA project. And I will be explaining what FPGA can be, how an FPGA project can be done from scratch, and you can take care of the design flow by yourself. So it requires a lot of experimenting. Initially, you will not understand everything, but eventually you will get the grip and you can proceed further. Okay, so I think I'm ready for the next question. We can discuss further.
So let us move to signal processing applications of FPGAs. So why are FPGAs considered as ideal platform for signal processing algorithms?
Yeah, that's a very good question. The thing is, when you talk about FPGA, I have already said that there are certain cases like mission critical applications, sorry, in which FPGAs are used. The reason being, FPGAs have this capability of reconfiguration, where they will actually allow you to upgrade the features or change the image, or the system itself upgrade it in such a way that the FPGA receives like, for example, let's take an example and illustrate this. For example, you are trying to use a radar, okay, and you are trying to process the radar signals, and you need to detect a target. So this particular algorithm was implemented in an FPGA. Assume that you have upgraded your radar hardware with a new set of sensor array, which is having higher number of sensors than the old array. I hope it makes sense.
Yes.
Now, what happens if you are using an MCU is that you will have to replace the MCU if the MCU doesn't support that much number of sensors.
Right, right.
But FPGA, that is the advantage of an FPGA. For example, if you are using a medium level MCU and concurrently you are using a medium level FPGA, that is where the advantage comes. That is, FPGA, you can actually, without changing any hardware, without even touching the hardware, you can actually change the image, reset whatever a new channel you have accepted, you can actually use it and further proceed with that. So that kind of a situation is better when you are using FPGAs. That is why I prefer when we are using a signal processing application, we use an FPGA. And also the mathematical modeling that we do for signal processing application comes into picture when FPGAs are used, because FPGAs actually improvise these models with their capability. So that is the approach that we should use.
What about GPUs? Actually, convolution like operations we do on GPUs, so that is also a kind of signal processing. So GPU versus FPGA, what are your views on that?
Main view is cutting the cost. GPU cost is very much higher than FPGA. And another thing is FPGA, the reconfigurability of FPGA is higher than GPUs.
Yes.
So that is the main advantage of an FPGA compared to a GPU.
Yeah. So can you share some real world examples of FPGA in signal processing?
Sure. So the first thing is based on my experience, I will share you. The first thing is I'm not describing any data regarding the projects, but I will just give you an illustration of what FPGA actually did in one of my projects. That is, I had to implement a highly parallel video processing algorithm. Okay, so it had to run in background. At the same time, it had to deliver some correction mechanism to the real-time video stream. So this signal processing algorithm had multiple modules, and it had to be implemented on a very small scale FPGA. It's a low tier FPGA. So you might have heard of Lattice. Lattice is one of the top vendors of FPGA nowadays. And I will tell you a few vendor names also in the end of the meeting, so that you can try out these FPGAs and their design tools. So Lattice FPGA was used. And the thing is, we had to implement, when we are talking about FPGA and signal processing, we have to have an understanding of linear algebra, because we are trying to sample the signal, we are trying to use matrix based convolution methods, and then we are trying to generate an output. So we should have a proper understanding of how we can translate one particular data and multiply it or divide it or whatever operation you are doing, convolution or convolute the signal, and then finally generate a continuous stream of sample data. So this particular design was done on an FPGA. But the problem we faced was that one of the IPs was not provided by the vendor. So we had to manually create one IP and then deliver the entire design. So that kind of problems may arise when you are actually delivering an FPGA. And then also one another problem in FPGA that can arise is resource. So when we are going for cheap FPGAs that are low power in nature, it has a resource constraint with which we can actually deliver a design. So you have to stick and optimize the resource as much as possible so that you have a better design with high performance. So signal processing applications is nothing but you're taking in a particular data, you are processing it in a different format, and finally you are delivering it in a real-time scenario. FPGAs are good for real-time processing also. So its bandwidth is actually that much good. So that's my suggestion on signal processing with FPGAs.
Yeah. Okay. Thank you. So, how do FPGA handle real-time data processing and parallelism in signal processing applications?
Okay, so basically, when we talk about FPGAs handling signal processing, for example, let's take one example. Okay, so why I always quote for an FPGA compared to an MCU? The reason is that assume that there is a requirement where you are processing one particular data at a one particular speed, and you need that data to be processed in a different format in a different speed. So this kind of approach, when we are trying to do, it is easier to do with an FPGA. And this can be done using a particular method called clock domain crossing. Domain crossing, okay, CDC. It's commonly called CDC. So when we have one design, for example, one filter is processing a data at 20 megahertz, okay, and we are actually passing it to a adder or some sort of a sequential device, not just an adder, some sequential device, and we have to have this working at 100 megahertz. So this kind of an approach, when it comes into play, we can implement both of these things in an FPGA, provide 120 megahertz clock, and in between we have an interface that will actually manage the CDC. So CDC can be managed in multiple ways, but this kind of an approach is actually important when we are using an FPGA. FPGAs can actually deliver higher performance in these kind of approaches, and that is why I'm more pushing more on the parallelism. Because if it was an MCU, you need two different MCUs or two different devices that are supporting the MCU for this particular speed, right? So that speed issue can be solved with the FPGA. That is how we do it.
Yeah. Okay. Yes. So we will
That's
have Q&A. I think in that we will cover all the questions which you are putting in the chat box. So let us now move on to the defense domain use cases of FPGA. So how have FPGA been leveraged in defense applications, particularly in the area of radar, communications, and cryptography?
Okay. In defense applications, FPGA, based on this parallelism, FPGA can be exploited in various applications, including electronic warfare. Then, we are using jammers. We are using aerial surveillance networks. Then, in sonar applications, in radar applications, in missile systems. We always hear a lot about missile systems developed by DRDO, and such as Agash, Agni, etc. So these missile systems also make use of FPGAs. So why FPGAs play a crucial role in defense system is that when we talk about a defense system, it is mission critical, right? So if it loses one particular element in a time, then for example, you have a particular constraint that should be responded to, or in milliseconds of time, or maybe nanoseconds of time. An FPGA is the best option that you can use because it is parallelly checking for all the conditions and scenarios inside the system. So mission criticality is actually validated there. And I also said about satellites, right? So for satellites, there is a particular section of FPGAs that are used, or division of FPGAs that are used. It's called radiation hardened FPGAs. So why radiation hardened FPGAs are used is that in outer space, when we have FPGAs that work in outer space, there is a issue with the radiation that is having occurring in outer space, because we are protected by ozone layer here, but outside outer space there is a high amount of radiation that is generated by the solar rays. So this can actually alter the functionality of the design or the device. So for this, they will actually use radiation hardened FPGAs, which will not toggle or cause any disruption in the digital design. So these kind of setups are used in FPGA, and the cost of a radiation hardened FPGA will be very much lower compared to a radiation hardened ASIC. And also the thing is that the manufacturing process timeline of an ASIC is nearly 3 years.
Right.
So for a particular application, you have to wait for 3 years to deliver an ASIC. In comparison and contrast with an FPGA that is readily available in the market, all you have to do is you have to generate one design, push it into hardware, and then send it to your mission. So this is the comparison. So that comparison itself makes it more easier to use an FPGA than an ASIC, right?
Yeah.
So that is why FPGAs have an advantage there.
Right. Yes. So, can you talk about how FPGAs support the development of secure and flexible defense systems?
Basically, the first thing is FPGAs can be programmed at any point of time. You can program it, reprogram it any number of times at any point of time. So, for example, you have a satellite, or I'm not talking just about satellite. You have a missile system. Okay, let's take a missile system. Now, let's go to a different example. You have a missile system. So, assume that you are delivering it, and on the midway, then someone tried to steal the entire device, and or someone hacked into your system and is trying to manipulate the entire system, for example. And in this scenario, what you can do is, if you erase the FPGA, then FPGA is nothing but a dead meat. It doesn't have any operation. It is nothing but a dead device with a number of CLBs and an interconnect. But in case of an ASIC, it will have so many data that has been backlogged inside, because it has a perfectly designed architecture, right? And it will have some instruction set also. So wiping is easy for an ASIC also, but the thing is, FPGAs can be wiped and reprogrammed very easily. And also, even if you don't know FPGA and you are the end user, if the people who are delivering the FPGA and the design, if they are actually giving you the bit file or the image file and the FPGA, you can yourself program it just by looking into a manual.
Yeah.
So it is always safe. You can keep the FPGA clean when it is not used, and when you need, you can program it and use.
Right.
So that provides one level of safety. Second level of safety is that the cost of ASIC, as I mentioned earlier, also is higher. So the manipulations made in an ASIC should be so much that it provides all kinds of threat-free functionality, right? But inside an FPGA, you can actually develop some methods that actually provide better, high quality security and safety threads. So this is how we work on it. So for example, let's take the case of an FPGA. You are designing a cryptographic communication system, right? So this communication system has so many layers, and these layers can be actually manipulated in different formats. Assume that a hacker came in and they are actually manipulating the by hacker, I should also inform you guys that hackers are not just for softwares. They can actually hack into hardwares also these days. So it's all over the news also. Many hardwares are hacked, many servers are hacked these days, and you can check for the history that happens with most of the servers these days. like bank servers. They are hacked into bank servers and they will put timers in such a way that the entire money can be looted within minutes of time. Okay, so these kind of approaches are there. So hardware hacking is another thing, and FPGAs can actually have reconfigurable, adaptable solutions for that. But whereas an ASIC cannot actually directly do that always on the time, right? For example, you found that this particular hacking happened recently with another device. Then you can actually add a particular algorithm so in your FPGA design such that it cannot be hacked. It is hack proof. So that kind of a security is available. You can reconfigurable it. That reconfigurability is actually adding more and more to the FPGA.
Yes. Okay. So let us. These days drones are very popular. So how do FPGAs play a role in that? Uh,
Basically, almost we have seen many videos in over all the social media networks about how drones are used. Recently, DRDO had tested one drone that was kind of attacking. It was an attacking drone. It will actually go and self-destroy itself by exploding at its destination. Okay, so in this case, you need to have precise control, and there will be algorithms that are working in parallel, and mostly these kind of drones will have AI ML support, right? So AI ML, mostly when we talk about AI ML, we all will have a figure in our mind, that is the neural networks, right?
right.
Neural networks, how they are formulated, they have multiple layers, and each layer will be formulating each different outputs, and finally we will come to a conclusion that this is the prediction of the system, right? So similarly, FPGAs can also do this because it is highly parallelized. So when you take the case of a drone, which is having a real-time detection and it should be controlled in a very precise manner, this real-time multi-layer approach can be actually implemented very easily using an FPGA. So if you take the case of most of the modern drones, there will be an FPGA that will actually deliver most of its parallelization in the design or in the working of the drone. Okay, so that is how they actually do things.
Okay. Yes. So let us now move on to the future of FPGA-based systems in defense and other industries. So how do you see the role of FPGAs evolving in the defense sector over the next decade?
I see a bright future for FPGA in the next decade because now even most of the mission critical devices, designs, systems are using FPGAs. Even if you search for the systems that are used in Starlink systems of SpaceX, or you check for autonomous driving cars or Tesla or even Indian systems, like recently Mahindra had launched BE60. It is a fully autonomous like it is fully automatic car that is electric vehicle, and it has some autonomous parking that they have included, and for that they were using around 440 sensors, and it is connected completely using one particular AI algorithm. So there are multiple FPGAs used inside the Mahindra car. So if you just imagine one particular Mahindra vehicle that has become so much trending, or a Tata vehicle that has become so much trending nowadays, is using so many FPGAs for actually delivering a high end, high quality, high performing product. So imagine what will happen in the near future. Now we are in petrol or ICE engine era, and near future it will change to autonomous vehicles. Electric vehicles will come up. Now even now it is booming. Battery systems will be there. So battery management is another thing. We need to understand how the battery is working fine or not, and for that also we can use FPGAs inside the vehicles. So these kind of things will be there. And even the car I am using, like it's a petrol vehicle. Even in that there is engine control unit which is having an FPGA. Like it will detect all the sensors all the time. It will continuously read. It will deliver. Like it will always keep monitoring, and that parallelization is what is giving FPGA the advantage. So in future, when more and more tasks have to be integrated to one particular device at a low cost, low power, high performance, high speed device, FPGA will come into play.
Okay. Yeah. So, what are the emerging trends in FPGA technology and how are they shaping the future of innovations in industries?
Yeah, that question I was about to discuss that. So most of us know that FPGAs are not just the CLBs nowadays. It has integration with SDKs. That is, in terms of software development kits are coming with FPGAs, where we can actually use the FPGA to be prototyping or using some software processors. Like you need to use a RISC-V instruction set architecture inside an FPGA. You can call for a software processor that will be provided by the vendor, or even you can make it if you are good enough, and then you can implement it on an FPGA and actually run an application based code in the FPGA itself along with your FPGA logic. So this will add on the FPGA's efficiency as a processor as well as an FPGA. So it will act as a hybrid processor. So now these kind of approaches are there. And also the another thing is that I didn't mention most of the vendors. So nowadays there is vendors like Intel, there AMD. AMD recently bought Xilinx in 2020, and then we have Lattice. Lattice is an emerging vendor. They have high performance, low power FPGAs which are very cheap. Then we have Microsemi. Then there are other companies that are working in defense applications. They have one or two FPGAs that are good enough to perform in satellites or missile systems. So, but they are very costly because they have that kind of like I earlier I said, radiation hardened mechanism is being used for those FPGAs. So these kind of FPGAs are there in industry now. And unlike in the beginning, FPGAs were having only the tool that was meant for designing the FPGA design flow only. You can only follow the design flow. But nowadays they come with the SDK. SDK means you can implement a parallel application processor inside the FPGA along with the FPGA components and then run this processor in such a way that it will work in a sequential manner as well as a parallel manner. So hybrid mechanism will be implemented in that. So this is what current trend in FPGA is, and it is growing. It is growing in the sense that it's growing drastically, and you know about Moore's law also. So FPGA, when the nodes are reduced, Moore's law is also taking up FPGA designs in a better way.
Okay, so let us move to. Can you discuss the potential of integrating AI and machine learning algorithms on FPGA platforms for autonomous defense systems?
Yeah, sure. I think I have already covered that, but I'll give you a brief understanding on that. Assume that you have a missile targeting system. Okay, you have a targeting system that targets a particular destination or a target which is located at a particular point far away from your origin. Okay. Now the thing is the missile should be guided, right? So the missile should be guided in such a way that it is having many parameters to be checked during its transit from point A to point B or the source to destination. So in such a scenario, the avionic system of the missile, the warhead of the missile, everything should be monitored, right? Speed, the velocity, everything, all the constraints, roll, pitch. There are certain constraints that we technically use in terms of a missile or a space object that is actually flying. So these kind of constraints will be monitored parallelly. So in that scenario, we need to have an algorithm that will work in the best way, providing the best results and providing precision in hitting the target with 100% hit rate, right? So this is done using AI/ML these days. So for that, we use FPGAs. So we will deliver this particular design as an AI/ML logic. Then we will, okay, I will give you an example on how we will design that. For example, we have an AML coding that is done in a Python or a software. Then we have a mathematical model with us now, right? So now the mathematical model is available. We will directly map these mathematical models into the FPGA based on the available resources. Okay.
Right.
So this graph or this AIML model is now mapped into the FPGA. And the advantage of AIML model is if you take one particular layer, it can be replicated, right? For example, you are trying to read something, trying to find a letter, a particular letter using a network, neural network. and you will have n number of ways someone can write a letter, right? For example, if I am writing A, the same way you will not write A, right? Or all these audience people, they will not write A. They will write in a different format. Their handwritings will be different. So for detecting this, the layers will have a different combination of writing A. So, but the fundamental element will be same. You have to detect A, right? So in FPGA, what we can do is we can write the code for one particular node and then replicate it in multiple formats. So what happens is you are reducing the number of lines you are writing. At the same time, you are generating a full layer. So if you have a four layer approach, then what you will do is you will be writing code only for four different nodes, and all the other will be replicated. So what happens is your effort is reduced, but you have a highly efficient system as the output.
Like,
So this is how we will be doing.
yes.
So that
Yeah,
is why FPGA comes into picture when these kind of applications are there.
like I would also like to add to it, like I have also worked on deep neural network design for FPGA. So in that we designed just one single neuron, and actually we designed a neural network of four layers. So we just we need not code all the neurons. We just
Yeah, exactly.
instantiated. Yeah,
There is a method with which you can actually generate multiple instances of the same module
yeah,
in FPGA. So if you are an enthusiast, you can actually work on that. It is called generate statement. In Verilog, it is called generate statement. In VSTL also, it is called generate statement. So you have to write the generate statement, and then you have to give a for loop, giving the number of iterations with which this module can be replicated or duplicated, and then it will actually duplicate. And for each instance, you can actually provide a different input. That is the advantage.
yeah.
So that kind of approach can be used in FPGAs.
So, how critical is it for India to develop homegrown FPGA-based defense system for applications like radar, electronic warfare, and avionics?
Based on the current scenario, it is very critical that we develop some system on FPGA, and we have our own fab lab. And I believe that recently the government has issued permission for Tata Electronics and Tata Semiconductors to set up fab lab and other related infrastructure in Gujarat and as well as Assam. So if you're seeking something, you can actually catch up with those industries and work around it, because they will be delivering one fab lab very soon. They'll be launching one fab lab very soon, and I believe that can be used and for maximum number of chip outcomes. But I don't know, it's still like a stronghold of China, because they have that hold over TSMC, which is the biggest and the best fab lab. And also with Samsung and Intel, they are the top competitors, and now Nvidia also has stepped into the game. So these fab labs, if we do not have hold, we have to depend on another foreign person, right? So that is another issue that we are facing. But it is critical that, based on the current political scenario as well as economic scenario, it is critical that we have to have a fab lab that will actually develop and deliver FPGAs and ASICs very soon in this country.
Yeah, in 2025, we are going to launch our first chip, right?
Yeah, yeah, correct.
Yeah. So
And
how?
also, you can catch up with CDAC and IIT Madras. They are also having a good design aspects on ASICs. They are working on Vega processors in CDAC and also Shakti processor in IIT Madras. So you can connect with these people. They are very good, excellent mentors, as well as excellent platform they are providing for any enthusiast who is interested in developing chips. And they are focusing on RISC-V architecture, so you can catch up with them also.
Yeah, I would like to add to it. You can search for Shakti on Google, and so you will find their page. You can apply for internships and as well as full-time positions also there. So you should consider that option.
Yeah,
And
and now coming to the final stage discussion about FPGA-based defense startups. So, in terms of space applications, there is a program that Government of India has launched. Department of Space has launched. It's called InSpace. InSpace program is a very highlighted collaboration between ISRO and private partners. and it is a high success, a huge success actually, because there are many organizations, many startups that have collaborated and they have delivered high class, high performance defense systems and space application networks and systems so far. So you can look into that if you are actually inclined to space applications. Now coming to defense applications, DRDO once in a year or twice, they actually have a Dare to Dream contest where they will be asking for ideas from startups, individuals, or academicians, or even students. So you can actually ideate something and then deliver it to them. They will actually provide funding if your idea is good enough. And also they have the Defense Ministry of Defense also is doing another challenge, which is called the IDEX. So the IDEX is also another forum where you can actually present and deliver one particular idea, and they will provide initial phase funding to you guys if your idea is that much good.
Yeah.
So you can start up. Yeah.
So, like, student have got into first year, so how she should plan to become a FPGA engineer since first year? What should be the right roadmap to learn FPGA?
First of all, understanding the VLSI basics is very crucial, especially the digital design. So, if you don't have a proper understanding of the digital design and how digital circuits work, how they can be interconnected and manipulated for developing and delivering a design, then that is first thing that they should focus on. Second thing is how FPGAs, because FPGAs you have multiple options. You have medium tier FPGAs, low tier FPGAs, high tier FPGAs. You have military grade FPGAs. So FPGAs are of different types. So let's start small. They can make use of tools like Lattice or Xilinx Vibado, and then they can try out delivering small designs and then trying simulating it, and then when they have a FPGA in hand, they can actually program it and test. But I would suggest, as we keep on going up the ladder, what we need in parallel is high amount of research data. So we should make use of IEEE, we should make use of Springer and other research documents in such a way that we can actually get more and more ideas and perspectives. And another aspect is, when we are as an FPGA engineer, I would suggest is that we should be open to all suggestions and criticisms from all the sides, because for a one particular problem there could be many solutions, right? If you are implementing, like I said earlier, full ladder, if I am implementing as a fresher and if I'm implementing as an experienced person, it will be different. So listen to people who can guide you, who can mentor you, and finally take it into your account and finally proceed with that.
Yeah. So, what kind of government-backed programs or funding opportunities exist for young engineers who want to innovate in FPGA-based defense applications? Like you told some, uh,
IDEX.
yeah,
IDEX is a program. I forgot the full form. It's
innovation
purely,
for.
yeah, it's from Ministry of Defense. So they conduct, even one challenge is ongoing right now in their website. So you can check on that. It is mainly for developing embedded systems and solutions for that. So you can actually check on that. And if your solution is good enough, they are ready to fund you for your startup and for your idea to be utilized as a prototype and finally as a product.
Yeah, and what are the different ways to get into DRDO?
Okay, now talking about the government jobs and private jobs of FPGA or VLSI. In private domain, you have a very specific number of jobs. Like if it is verification, you have verification job. If it is design, you have design job. If it is testing, it is testing job. Validation job. But in terms of government organization, it's not like that. Whatever your background is based on your studies, that is basic level screening of the domain in which you are going to work. Like if you are a VLSI engineer, you can work either in ASIC or FPGA, right? So that kind of thinking will be done when screening will be done in government systems. But in terms of private, it will not be like that. They will be selecting you based on your skill in particular domain. Like if you are FPGA engineer, you are FPGA engineer. If you are an ASIC engineer, you are an ASIC engineer. So that kind of a thinking is there. And the methods to get in corporate world, it's pure like you are attending interview, you are getting in. But in government, there are various approaches. For a graduate, you can write GATE, get into DRDO. For ISRO, it is ICRB. They have this ICRB exam. They conduct once in a year. It was conducting. It was like that only. So once you clear the ICRB exam, you can actually sit for the interview, and then your selection will happen as a scientist, come engineer. In DRDO, GATE will be there as a first screening level. Second screening level will be their test, which is descriptive in nature. And finally, there will be an interview, and you can enter as a scientist B. So scientist, it is a first level of scientist you can enter, and that is a first method in for graduates or near graduates. Now, talking about experienced people, you have lateral entry schemes in ISRO as well as DRDO, and other organizations such as HAL, HAL, BHEL, BEL, etc., where they will be calling you based on your experience. And you can actually look out for the notifications from employment news or some like it's called Rozgar Samachar in Hindi. I think it is coming from publications division of Government of India. So that employment news can be a crucial element that you can search for jobs in government systems. And there are other organizations also, like BrahMos is there, Bharat Dynamics is there. So these organizations all call for lateral entries. So you can actually look out for these jobs also
Yeah,
if you have missed the opportunity as a graduate.
yeah. And these days, many private startups are coming up. So
Yeah,
not only we don't have only just government jobs, we have lot of private sector opportunities as well. Like
correct.
Skyroot Aerospace, we have in defense also many good
Yeah.
startups coming in. Yes. So let us now move on to Q&A. So, so what? So Mrinal have asked that does CDC issue occur on synchronous design?
CDC issue occur on synchronous design. It is possible based on the design. The CDC is basically when you are actually delivering one particular data or a signal from one point to the other, and there's a clock domain mismatch. But if most cases, if the clock is actually generated from the same source and it is actually a multiple, it can be covered up. But if it is not a multiple and some manner you have not generated it from the same source, it can actually occur. So in synchronous design also it is possible based on how good designer you are. It is possible. Like if you are a good designer and you have covered all the corner cases, then it will not happen. But if you are having some corner cases that was opened up, then it is possible. And it is always good to cover up all the corner cases before proceeding for a final delivery of the design.
Yeah, so how final layout GDS is affected without CTS? Change in layout of ASIC after addition of CTS.
How final layout is affected without CPS. Change in layout of ASIC after addition of CTS. Okay, so CTS is important because, as I said, CTS actually this kind of approach was actually taken into consideration because the timing issue was very much bulky in terms of when we were doing clock tree along with the normal routing procedure. But when it came to clock tree being routed separately using CTS, the advantage is that we can reduce clock skew. I believe most of you might be understanding based on static timing analysis that clock skew. What is clock skew? Clock skew is nothing but if you have two particular devices working inside a design and you are generating a clock that is supposed to reach both these devices at the same time, and there's a mismatch in this arrival time of the clock at both these devices, then that is called skew. So it can be positive, it can be negative based on what is the position or hierarchy of these devices in the design. So based on this question, I would like to tell you is that we should do it parallelly with the physical design, and then only we can proceed with the layout. Because otherwise, what will happen is later stage we cannot actually fit in the clock tree in a better manner, and timing issues will be higher on the higher side in ASIC. Right? FPGA, that kind of an approach is not necessary because there is no separate clock tree synthesis method. Even though clock routing is done, it is not. It is actually done on a fixed interconnect interface. Not we are not actually developing an interconnect interface in between modules like we do in an ASIC. So that is very crucial. I think that answered you,
Yeah.
Pranav. Yeah.
So any more questions? So, okay, I think these many questions only. So, if you still have any doubts, we have Anand as a part of our community. So, he will guide you with your queries if you have any further queries.
Yeah, sure. I'm in the WhatsApp group as well as I'm available. My contact is available with Anushka. So if you have any queries, you can actually directly post it in the group, or you can contact Anushka. She can connect you with me. So I hope I try to make it as much as friendly as possible. But as this is my first podcast, I think I try to deliver it in a very fast manner. I will try to improve in the next podcast,
No,
and I hope you all. Yeah.
Anand, it was very good.
Oh, thank you, sir. Thank you. Thank you so much.
It was very good. Okay.
Yeah. Yeah.
Yeah,
Basically, I tried to. Yeah. Yes,
just
sir.
build upon it. Just build upon it. But it was very good.
Thank you. Thank you so much.
Like, I had one thing to ask, like, can you give a month-wise breakup, like, for a roadmap to learn FPGA, like, in 6 months learning journey or something like that?
Sure, sure. I can actually give you that support right away. I'll give you a roadmap that is very brief. First thing is that you should understand how to analyze a specification. If you have a problem and you have specified the solution in such a way and you want to translate into the hardware, the first thing is how to analyze the specification and how you can actually map it to the mathematical model. This you should have a clear cut understanding. And second thing is, based on the understanding and knowledge of your digital basics, you should have the capability of translating this mathematical model into the digital design. Okay. So digital design, in the sense, I am a person who sticks to pen and paper still. Okay. So if you have a method where you are actually implementing an algorithm and you have already implemented it in MATLAB, and assume that it is a filter. I have already discussed with Anushka regarding a filter recently. So filter will have multiple inputs, right? Multi-channel filter are there, single channel filter are there. So that kind of thought should be coming inside our perception. So it should actually be there in our brain, and we should be able to visualize all these things. And then we should understand first filter input should go into this particular module. Second filter input should go into this particular module. And finally, we are developing this filter. So that kind of a perception should be there. And so initially, I would suggest you to create golden reference models using softwares, that is mathematical modeling. And I'm not asking you to study every software. I'm asking you to study a software that is comfortable for you. Either it is MATLAB, CPP, or LabVIEW, or Python, anything that is comfortable for you. You study and you try to implement a golden reference model, especially when you are designing an algorithm. Then once you are clear with how the algorithm functions, you have the specification, you have created the algorithm model. Now you are very much clear about how the algorithm functions, right? So once that clarity is there, you are good to go for the RTL. So, and RTL, you are having this particular FPGA. So now you know how many IOs are there, how many CLBs are there, how many DRAMs or memory blocks are there. So you know the constraint of the FPGA. Now, with that constraint in mind, you should proceed with the RTL design. Okay,
Yes.
you should think about that also. You should work like an FPGA. That is what I am trying to say. You should work like an FPGA. You should think about how the FPGA will work, and finally, you should map it to the FPGA using your digital knowledge, digital domain knowledge. So that is how this is going to work out. And as a starter, you can work out with Xilinx Vivado. Xilinx Vivado is the best option I will suggest personally from my experience. It has a good GUI. It has a good tool flow. Everything is integrated into one tool itself nowadays, and it also has AI/ML support. The latest version has AI/ML support, so you can actually use it for your future also. So you start off with Xilinx Vivado and slowly build small designs and understand what is the number of inputs, what are the how you can establish a connection. And for designing RTL, you need to have a proper understanding of Verilog. So I would suggest Verilog as a start case. VHDL was good, but Verilog as a start case. VHDL is commonly used in defense even nowadays, but Verilog is the most common industry language that we use. So Verilog, if you have a doubt and if you want to have a tutorial, you have a good course in NPTEL I remember his name. I couldn't actually recollect. He's a good professor from IIT. He's actually taking Verilog courses, and you can take his classes. It's around 64 videos are there. You can take the class, you can understand Verilog thoroughly, and then you can proceed. And his videos, the advantage is that he's giving you assignments in between. You can actually check it. Yeah, Indra Nielsen. Thank you so much, Nana. That Indra Nielsen sir is superb. His classes are world class, and I will suggest him only. And for timing analysis, you can suggest. I will suggest you one particular book. It is called J. Bhaskar, and even for Verilog also, he has one textbook. J. Bhaskar. I will put it in the chat. His name is J. Bhaskar.
Yes.
So you can actually make use of his books. He is very good in VLSI domain, and you can make use of his books. Static timing analysis for nanometer designs. So his books are very good for timing analysis also. If you are encountering some timing issues in your design, you can refer to his book. Super. So these kind of things you can refer and try to do research and try to think and try to take an input from other people so that you can question your own design and iterate it further and improve it. Okay. So don't stress yourself when you are trying to design first design. You are writing 50 lines of code. Oh, this is too much, and it has consumed 2 or 3 VRAMs. It is very big and huge. Don't think like that. It's okay. You will improve over time. So in 6 months' time, what I will suggest is try to understand how you can model something mathematically from a specification, and also try to learn the HDL. So once this is done and your digital design basics are also good, you're good to go for an FPGA design career or courses like that. And many courses are available.
I would like to add something to it. Like Xilinx FPGA is very costly, so these days Kunal Ghosh, VLSI system design have bought a latest semiconductor FPGA board, like 2600 rupees only. So that's a very good option for beginners. Like Xilinx FPGA cost around 15,000. That's
That is a good option. But based on what I suggested is because I'm working currently on Lattice and Intel, and only for my personal research projects I'm doing Xilinx. But based on why I suggested Xilinx is that everything is in the particular GUI itself. You don't have to go for model sim, like simulation. You don't have to go for model sim or Questa sim. In Lattice, that is not available. You have to go for model sim and Questa sim again. But in Xilinx, that GUI itself has simulator, it has linter, it has hardware programmer also engraved in the entire tool as a single GUI. So that support will actually make it better for you to do things. It will not make you creepy. That is what I'm trying to say. And once if you are not using any vendor specific IPs, you can do it in any tool, right? Like you are not using a filter IP that is developed by Xilinx, then you have to do with Xilinx tools only. But if you are not using that and you are developing your own filter code, you can put it in any FPGA and run it, right? If that supports if that FPGA supports it.
yes. So, Veena, I have a question. FPGA don't we draw microarchitecture before RTL coding?
Yeah, that's exactly what I was trying to mention. That is, we have a mathematical model. We will actually model the mathematical model into the digital design as an architecture format. And that is exactly what I'm trying to convey. That is the step before RTL coding. We should have this architecture in mind. We should try to understand how we can actually implement the mathematical model as a digital design. So that is actually providing the architecture.
Yeah. Okay. So I think it was a very wonderful session. We got to learn a lot of things. So if you still have any queries, you all can ask
Yeah.
me.
Ananth, where are you working as of now?
I'm working with Eviden, sir. Eviden is an Atos company. It is a French MNC and it's in Bangalore.
Where in Bangalore?
Whitefield.
Oh, Whitefield. Okay.
Yeah.
Can you, Anushka, can you please share his LinkedIn profile? Anyway, I can also search, but just to be sure.
Yeah, can you give your LinkedIn profile?
Yeah, sure. One second.
Yeah, if you can put on the chat.